So let's start talking about continuing where we were on ordinal logistic regression. Okay. Now, just to remind you, for most of the class last time we talked about Polytomous logistic regression. And both Polytomous and ordinal logistic regression involve a logistic model where you're dealing with an outcome that has three or more categories of the outcome. And when you're dealing with Polytomous logistic regression, the categories aren't ordered. So when you're using Polytomous logistic regression, you're going to get as many odds ratio as one less the number of categories. Well, odds ratios is you have one less the number of categories. There's usually a referent group. You have to decide on a referent group, and then you'll get an odds ratio that compares each of the other categories to the reference group. And so if there are 5 categories, you'll get 4 odds ratios. And we looked at what the model looked like. We looked at the general formula for the model. We looked at some examples. We looked at the odds ratio formula, and we looked at some examples where it was calculated or the computer did it. We showed how the computer program works or how proc logistic works. And the key thing with proc logistic, if you want to use Polytomous logistic regression, is what you have to do is you have to add this glogit, link equal glogit, to the code in order to make sure that the computer does Polytomous logistic regression. And it turns out we'll talk now about ordinal logistic regression, continue a little bit from where we left last time, and I'll show you what the code is there and what the output looks like. Okay? Any questions? Questions at this point? Okay. So the example I started talking about was this example dealing with, again, this word that I can't pronounce very well, and I keep trying, acinetobacter. Did I do okay on that? After 10 tries. Acinetobacter bacteria, and it's resistant to Acinetobacter. Okay. That's the outcome. And actually, that's not the outcome. The outcome was 3 categories of the length of stay that a person was in the hospital. Okay? And the key, and it was if you remember, it was a retrospective cohort study that involved matching. Okay? But it wasn't a matched case control study. Okay? It was a cohort study that involved matching. The exposure variable was whether or not a person was either resistant or susceptible to this bacteria that I can't pronounce. Okay, so this exposure variable is called AC status. So AC, okay, as opposed to DC. AC status. Okay, and the outcome is ordinal hospital days in length of stay in 3 categories. Okay, and then there were some other variables. Well, first of all, there was this matching variable. People were the susceptibles were matched to the resistant persons, cases, on how long they were in the hospital prior to their getting infection. As long as they were within 5% of the number of days that they were in the hospital, they were considered to sort of be at risk for roughly around the same amount of time. So there was this exposure time variable that was the matching variable. Okay, and that variable was defined if there were 3,000 people in the study. Well, actually, 3,000 people in the study originally. No, wrong study. As you can see, there are 112 people in this. I can't even read. 112 people in this data set. Okay, there wasn't pair matching. And in fact, matching was pooled into groups, into 8 groups. And that allowed us to avoid, allowed the analysis to avoid having to use a conditional maximum likelihood approach, which wasn't available for the ordinal logistic regression approach that's in proc logistics. So that's why there were not eight exposure time categories that allowed us to get around having to do something that we couldn't do, which would have been using conditional logistic regression. It allowed us to do unconditional logistic regression. Then there were two other variables called Apache and Charlson that were other control variables. So these three variables, new x time, 8 categories, this Apache variable and the Charleston variable, which were both continuous variables, were control variables. And the exposure variable was AC status, and the outcome was length of stay. And we started looking at this table. That's what we were looking at, which is a 3x2 table that describes the relationship, the crude relationship between exposure and disease. Doesn't control for the other variables. Okay, that's what we started looking at. And what we then did with this table was I showed you in the second slide here, this next slide, where I formed from this 3x2 table two 2x2 tables. I sort of cut the 3x2, I cut the pie into two sub-pies, you might say, or two pieces of the pie, that both of which involved the same number of subjects. But in order to do this, the first piece was I combined the 2 and the 1 rows into a single row. So 24 and 16 were 40, and 13 and 23 were 36. Compared that to the last row, to the reference group. And then to get the second table, I combined the 0 and 1 groups and left the second group. So I have these two tables, okay? And I think I mentioned a table that I didn't do. There was one other table I could have done. I combined 1 and 2 versus 0 and 0, 1 versus 2, but I didn't combine 0 and 2 versus 1. I could have done that, but I didn't do it. And the reason why I didn't do it is because if I did, I'd be breaking up the ordering, 0, 1, 2, 3. This way I'm keeping the order. 1, 2 versus 0 or 0, 1 versus 2 is still comparing two groups where it's keeping the order. But looking at 0 and 2 versus 1 is breaking up the order. And that would be incorrect in terms of the way one would do this, set up the crude analysis. Now, for each of these tables, we're right near where we ended last time, that for each of these tables, you can get it's a 2x2 table, so you can get an odds ratio. And for this table, the odds ratio was for the first one, it was 1.39. For the second one was 2.48, okay? And what I say over here on the right-hand side is what these two odds ratios, you would expect them to be approximately the same if you were going to be able to use this approach called the proportional odds approach to do ordinal logistic regression. That's the approach that I'm going to describe. There are some other approaches I mentioned, but this is the only approach that's proc logistic allows you to use, the proportional odds approach. There are some other approaches. In fact, another approach you could use if you decided that none of the other approaches for dealing with ordinal outcomes, an ordinal outcome worked, was to use Polytomous logistic regression. But if you use Polytomous logistic regression, when you really had an ordinal outcome and you had an ordinal approach that did it, you might be losing something. You're losing some efficiency, not taking into account the fact that there is some ordinal, there's this ordering in the outcome that maybe will make your odds ratios and your tests and your confidence interval more efficient. So in any case, we look at these two numbers, and these two should be approximately equal, and they're not. They look very different, okay, as we said last time. And as a result, this suggests that if you took this data and just did the crude analysis, it wouldn't be appropriate to use the proportional odds assumption. That's what this suggests, okay? Okay. Now, as it turns out, this is the crude, again, and what I'm showing you is the crude data. Okay, I'm not controlling for the other variables, the three other variables that we wanted to control, that the investigator wanted to control for. So if you really wanted to assess whether the proportional odds model was appropriate, what you'd want to do is to do an analysis. Even if you're going to split up the pie into subtables, you'd want to split up the pie to take into account the variables you want to control for, not just doing the crude thing. And if you did that, it may turn out that the tables that you get when you split things up, there'll be a lot more tables, okay? But it may turn out that when you start looking at the odds ratios you get in those tables, it may turn out that they actually are equal. The ones that you need to compare are equal. And so it may turn out that when you consider what they wanted to consider, the variables they wanted to control for, maybe the proportional odds assumption is okay, even though it doesn't look okay here. And as it turns out, as I'll show you very shortly, when you do this way of considering the other variables, the ones you want to control for, it is satisfied. The proportional odds assumption is satisfied. And the way you actually do this is not by doing a more complicated split up according to the variables. There's the test for this. It's called the test or the score test for the proportional odds assumption. So you do this test, and you do this test. If you've got other variables you want to control for, you put into this test some information that reflects the other variables, not just the exposure variable and the disease and the health outcome. And that test may turn out to be not significant, even though when you did the crude analysis, the test might be significant, or these two odds ratios, as you can see, are very different. I don't know if you got what I say. Well, just to make it clear how things might work nicer, here's another table. And I said a hypothetical example. This isn't the data, made up some data. Okay. So here's a different table that maybe they didn't get this table, I just made up this table. Okay. Okay, now if you look at this table, it's got 275 people in total, whereas the previous one had 112, but I'm just making up some numbers. If you took this table and you split it up into the two sub-tables that I did before by combining things the same way, 30 and 20 or 50, 30 and 70 or 100 versus 25 and 100. I'm doing the same thing, but now I have a different set of data. If I do that and compute those two odds ratios, what do you notice? They're very close, 2 and 2.06. So this is the kind of situation that if you got it and you were only looking at the crude data, this would be the kind of situation where you would expect to see the proportional odds assumption satisfied. This is a good situation for using that model. Whereas this one isn't, except that you could criticize making the decision that you can't use the proportional odds model. You can criticize it because you haven't controlled for anything. You haven't controlled for anything either, but at least this looks pretty good. Okay, so that's the hypothetical example. Now, let's talk about this test, the score test. Okay, and that's built into when you run proc logistic to do ordinal logistic regression using this proportional odds model. That test result automatically comes out. You automatically get that in the output. Okay, so you can look at that result, and it's a chi-square statistic. I'm not going to talk all about the theory, but it's a chi-square statistic that's approximately chi-square. It's assumed that with a reasonable data set, large enough data set, it's approximately chi-square, and the degrees of freedom is given by this expression, S times K minus 2, where S is the number of predictor variables in the model, and K is the number of ordinal categories of the outcome variable. Okay. Now let's go back to this. Okay. So what's K? Is that what I said? K? K. The number of ordinal categories. How many ordinal categories are there? 3, right? So go back to this thing. K minus 2 is 1, right? So what's S? The number of predictor variables. Well, if you're just using the crude data, whether you're using the hypothetical example or the real example, then just the crude data, there's only one variable in there. And it's a binary exposure variable. So S is equal to 1, right? So what's the degrees of freedom? 1 times 1, so that's a chi-square with 1 degree of freedom. So if you're going to do this test with the crude data, you get a chi-square with 1 degree of freedom. Okay. Now, if you're going to do this, so as I say, for the ordinal 3x2 table, in table C, C is this hypothetical example. You see, I say table C, and then I form table D, these two subtables from it. The score test is equivalent to testing the null hypothesis that the two odds ratios being estimated by collapsing one or more of the rows of the table is that these two odds ratios are equal. Null hypothesis is that the proportional odds assumption is satisfied, or alternatively, if you're just using the crude table, the crude data, and that's all, and you're not considering anything you want to control, and you're not controlling for anything, then another way to state the assumption is that these two odds ratios are equal. That's the null hypothesis. So then you use the program, or you use whatever the formula is, which the program does, and you compute this chi-square, and it turns out the chi-square for the hypothetical data, the value is 0.0082, and the p-value is 0.9281, which says what? Very non-significant, okay? So if I was using this data, the wrong data, the data that I don't have, but I made it up, so that if I use this data, and all I have is the crude data, this would be fine. That's all I wanted to use. If I wanted to use the real data, and I wanted to use that test, I wouldn't get this value. In fact, I don't think I actually ever computed it. I might have computed it somewhere and put it in one of the chapters. I mentioned that there were two, I think I mentioned, that there were two resources, two chapters that I've written related to Polytomous and ordinal logistic, well, particularly for ordinal logistic regression. There's a chapter on ordinal logistic regression in your logistic regression model book, text for this course, one of the two texts for this course. And there's also a chapter on combining Polytomous and ordinal into one chapter in the other book, the regression text that you had last spring with Bob Lyles. And in that text, this example and including the hypothetical example are described in there. So there's so the slides that I'm showing you with this example, and even with the example I used for the Polytomous, come from the other text, the Kleinbaum, Cooper, Nizam, and Rosenberg text. But anyhow, so it turns out that if I use the score test for the AC data, S is now not 1, because I got more than one variable in there. Okay. In fact, if I look at the variables that I'm considering, I have, this is 1. I have this variable new x time, which was a variable that had 8 categories. So I have 7 dummy variables, right? For the 8 categories. So there's 7 variables for that variable. 7, 1, 8. This is 1. There are 7 variables for this one, and then there's these 2 other variables that are in the model too, the no interaction model. So S is equal to 10. S is equal to 10 in this case. So I'll go back to this. S is 10, K is still 3, okay? So the chi-square test, the degrees of freedom for the test, if I actually want to consider the variables I'm controlling for, all the variables in the model, it's going to be a chi-square with 10 degrees of freedom. So when I look at the output for the proportional odds model for the real data, it's got to be tested, the proportional odds score test is going to have a 10 degree of freedom. It turns out that, this is it, there it is. Turns out that the chi-square happens to be, turns out when I run the model, I'm just showing you it, is 8.7459, the degrees of freedom is 10, and if you go to tables of chi-square and you look up to see the p-value, this is the p-value. Highly non-significant. The null hypothesis is that the proportional odds assumption is satisfied. That's the null hypothesis. This says you don't have evidence to reject the null hypothesis. So if you do the score test and it's non-significant, you have support for doing ordinal logistic regression using this model. And that's what this says, okay? So even though the two unadjusted odds ratios shown in the table that I originally showed you are different, we can nevertheless justify from the score test that the proportional odds assumption is satisfied for these data if you want to use these other variables, want to control for these other variables. Okay, that's what I've done so far. Now, let's go a little further. Now, the next thing I want to show you is what the proportional odds model looks like. And this is what the formula looks like if you're just dealing with the crude data, where you only have one predictor variable, one exposure, you're not controlling for anything else. This is what the formula looks like for the proportional odds model that is assuming that something about, we have to explain this, we have to explain what we mean by proportional, but this is what the model looks like. Now what's different about, well, what's similar to this, to the original binary, logistic regression model, the right-hand side is similar to the binary logistic regression model, isn't it? Isn't it similar? It's 1 over 1 plus e to the minus something, right? That's what the formula for binary logistic regression. However, it differs because the intercept has a subscript. Whereas when you're doing binary logistic regression, it's just alpha, right? It's not alpha sub g, okay? And the g has to do with the number of categories you're talking about, the number of ordinal categories you have. And the g is the g category, is what it stands for, okay? Now, this is similar, this formula is similar, but it's not exactly the same. So that's one of the differences. Now, the other difference is on the left side, right? It doesn't say probability D. Remember when it was binary? It was probability that the outcome was equal to what? What was it for the binary one? Probably that D was equal to 1. You either had a 1 or a 0. And now it's got something different. It's a probability that D is greater than or equal to G, where G takes on the value either 1 or 2. Takes on these two values, 1 and 2. In fact, in our example, the AC example, there were 3 categories of the exposure, and they were coded as 0, 1, 2. Okay? 0, 1, 2. That's the 3 categories. Okay? So if you look at this formula, okay, now if we're talking about the probability that D is greater than or equal to 1, there's only 2 possibilities. 1, greater than or equal to 1. What are we talking about? There's 3 categories, 0, 1, 2. So if D is greater than or equal to 1, what are we talking about? Could be 1 or 2, right? Can't be 0, right? Now what if instead the G was equal to 2? If D was greater than or equal to 2, what category or categories are we talking about? Only the last one, category 2. So when G is equal to 1, we're talking about 1 and 2. And when G is equal to 2, when G is equal to 2, we're just talking about 2. Okay. So, that's something that explains, that says it's different. This is one of the things that's different. And another thing that's different is that since you now have more than one alpha in the formula, turns out there's a relationship between these alphas. And alpha 1 turns out to be in this formula is greater than alpha 2. Now, I'm going to explain that with a little math, with a little algebra, to explain why that works. But in a sense, something has to work. There has to be something to reflect the ordering in there, and this is where the ordering comes in. This is something that the ordering comes in the alphas in this formula. We'll talk about it. We'll illustrate this. But another thing to point out about this formula is you notice, look at the formula, the expression for the coefficient of the exposure variable. Okay? If you look at that expression of the coefficient of the exposure variable, what you don't see that you saw in the Polytomous logistic regression model, you don't see a subscript G for the beta term. This is beta, not beta sub G. Okay? There's no subscript. There is a G subscript for alpha, but not for the beta. Okay? Now, I don't know if you remember this, because we only did it 2 days ago, but, maybe you're up to speed on this thing, but when you did ordinal logistic regression, well, we talked Polytomous logistic regression, remember you got more than one odds ratio. You had for each category, you had an odds ratio that compared with the reference group, right? So you had an odds ratio for 2 versus 0 and 1 versus 0, okay? So you got 2 odds ratios if you had 3 categories. How many odds ratios are you getting here? It's getting 1. It's getting 1 odds ratio. Now, one issue is, what is that odds? What does it mean? So we need to talk about that a little bit. But when you do ordinal logistic regression, you're not comparing 2 versus 0 and 1 versus 0. You're getting a single odds ratio that doesn't compare something to a reference group. Okay, so we got to talk about what that means. Okay, so that's what I say. The coefficients of the predictive variables, there's only one here, are not subscripted by G. So any odds ratio for this model, in this case, this odds ratio, doesn't depend upon G. Okay, that's another way of saying, but we'll see it more explicitly, what we mean by the proportional odds assumption. The proportional odds assumption is one way of saying that when you use this model, you're only going to get one odds ratio or a single odds ratio for any expression that you want to have about the exposure variables of interest. You're not going to get several odds ratios. And as I said, G equal to 1, 2 corresponds to the 2 by 2 tables that can be formed from the crude 3 by 2 table for these data that we did by splitting up the pi. That's why G 1 and 2 has to do with this way of splitting things up that we did over here or over here. There are 2 tables like this. Okay, now here's some computer code. Next thing. Well, one thing you want to know is, this is a little tricky getting used to this model, but let's look at the code. How do you do this if you had the data? Okay. Now, this is a way to write the code for the data that I have, because the data, and I'm actually, what this says here, this is for table C, that's the hypothetical data. Okay. Now, you notice that I just have, how many lines do I have? It says data simp, input, and then I got cards, or I could have said cards. We used to have cards, and now you put in, what do you put in? Data lines, okay. And then there are 6 data lines. This is the first one, this is the second one, the third one. I could have put this on the next line. 6 data lines. 6 data lines. Now you remember the table for the table C? Table C had 6 values in there. So I'm putting in a table line for each of the 6 values in this table, the 20, 30, 30, 20, 30, 30, 70, 25, 100. And those are the 6 values, 30, 70, 120, 30, those are the 6 numbers. So what are these other numbers? The 2 and the 0 and the 1 and the 0? That's distinguishing from the table whether somebody was either had the health outcome or they had the D was equal to 0 or 1 or 2, or whether they were exposed or unexposed. So these 6 lines are describing all the data in that 3 by 2 table, and the way it's doing that is the very first line of this is counting the number of people in that particular cell. In other words, there are 6 cells. There are 6 cells, and there's 20 people in this cell. There's 30 people in this cell. So each of the numbers, 20, 30, 30, 70, 20, is sort of a frequency count. So, and I think at some point when Eli was reviewing logistic regression, there's a way you could set this thing up where you have a frequency count. So all the data is described in here. And then it says input FRDE. FR stands for frequency. The frequency variable is the variable that describes the 30, 70, 120, 30, 25. The D is 210, and the E is a 0, 1 variable. Okay? You put the data in, you then say run, and then you write the code for running the model. So this is the key part. This is just putting in the data. Key part says proc logistic descending, just like we one way of doing it, descending, to make sure that the outcome is not the zero, but the higher number. Data, that's the name of the data set, SIMP, simple data set. Model, D equal to E, what does that say? The outcome variable is the D variable. The predictor variable is only one, and that's the exposure variable. And then by putting in the FR, I'm telling the computer that I have 70 people like this, or 30 people like this. So I'm counting the people, and then I say run. Now, one of the things you may notice about this code, and I'll show you the code soon for the real data set with the variables we're controlling for, but one of the things you may notice about it, differing from the Polytomous logistic regression approach, is that when we did Polytomous, what did we have to add? G-logit. Do you see that here? No. So when you're running proc logistic to do ordinal logistic regression, there's no G-logit statement. In fact, if you run this, there's no G-logit statement, it looks like what you're writing here is what you would normally write if you were just doing binary logistic regression. I mean, you're doing binary, it looks like you're writing doing a binary logistic regression, except you have some frequency, you're counting the frequency in the cells, and instead of having 4 cells, you have 6 cells. Okay. So how does the computer know when it sees this and it doesn't see G-logit, that it knows it's got to do ordinal logistic regression, which is the other option, instead of binary logistic regression? How does it know that?
The outcome has more than 2.
Yeah, who said that? Daniel, okay, yeah. Because there's more than 2 categories. So the computer is automatically going to do ordinal logistic regression if it turns out when it looks at, in some theoretical way, conceptual way, when it looks at the outcome variable and sees that the outcome variable is not just a 0, 1 variable, it has 3 categories, or more than 3 categories, it's going to automatically do ordinal logistic regression. So when it doesn't have G-logit and you've got more than 2 categories, it'll do this Polytomous proportional odds ordinal logistic regression approach. Okay, so that's the code for that. In fact, if you run this code for this hypothetical data. For the hypothetical data, you run this code, you get this information that I've got on the screen. Okay, look at the top of the screen. You see that? What does that say? Score test. So you get the score test right away. Now this is the data that I only showed you crude data. I didn't really have any other variables I was controlling for. Okay, and for this, these are the numbers I showed you. The chi-square was 0.0082, and the p-value was 0.9281, highly non-significant. Okay, so that's this table C, the hypothetical data, satisfies the proportional odds assumption. There's no other variables we're controlling for. Now, notice the output over here. Notice the output. What's different about this output, different from the Polytomous output? Well, you see 2 intercepts. Well, you know you're going to get 2 intercepts because you got alpha sub G. But how many coefficients do you have? How many estimated coefficients do you have for the exposure variable? 1, because that's what the model says. You don't have a different coefficient depending upon G. It doesn't depend upon G. So you only get 1 of these. Okay, and then what either I think it automatically prints this out if you just write the code that I showed you, and I didn't even write RL for risk limits or getting the confidence interval. It automatically gives you this odds ratio estimates. Okay, and look, it says E because that's the only variable in this model. So you're only going to get you're not going to get an odds ratio estimate for the intercept. Just going to get it for E because the intercept you're not interested in that. And you notice it says 2.023. So what's that? Well, that's e to the 0.7044, right? E to the beta. So the formula for the odds ratio in this model is e to the beta. That's the formula for it. Just like you would do e to the beta in a binary logistic regression model. It's the same formula. Okay? So what is this? 2.023. What is it the odds ratio of? Okay? It's an odds ratio. It's an odds ratio for the effective exposure on the outcome, given that you're doing ordinal logistic regression using the proportional odds model. Is it significant? Well, yeah. Or yeah, right? It's significant. If you look at the confidence interval or the wall test for it, you could even do a likelihood ratio. If you wanted to do a likelihood ratio test for it, how would you do that? How would you do the likelihood ratio test? Well, you'd fit a model where you drop E. You just have the two intercepts. And you get a log likelihood statistic for the model that only has the intercepts. You subtract the two, and it would be degrees of freedom what? What would be the degrees of freedom? Not 2, it would be 1, because there's only one variable you're dropping. There's only one coefficient you're dropping. So you can do a likelihood ratio. The wall test is significant. I didn't do the likelihood ratio test, but I've given you one of the two log likelihood statistics. Are you following me here? I hope you are. This is not that, but I'm not sure. Maybe I'm just talking to myself, So now let's say a little bit about the 2.023. Okay, this is important to say. You see these two numbers here, 2.2.00 and 2.06. See those two numbers? And then the number I just showed you from the output was 2.03. What do you notice about that number? It's between those two, right? Was it 2.03? Is that what it was? I keep going back and forth. 2.023, 2.02. It's between those two numbers that you got for when you cut the pie in those two ways. So what are you getting when you do ordinal logistic regression? You're getting the average, some weighted average of the two odds ratios you can get when you cut the pie in a number of different ways. And no matter how you cut the pie, you basically, each way is giving you the same odds ratio. That's what's being assumed. Doesn't matter how you cut the pie, that's where the ordinality, as long as you keep the order, the ordinality when you cut the pie, you're getting the same odds ratio. And that odds ratio you're going to get is an average of whatever odds ratios you get. That's what it means. Okay? One, a single odds ratio that allows for the ordinality. So that's what you're doing. Well, that's what it is. Now let's go a little further. Go a little further here. Look at this. This is the code for the AC data. Right? Code for the AC data. Proclogistic descending data equal to AC in B. Class. Now, you see this variable new x time? I've defined it as a class variable. What does that mean? Again, that means the computer is going to define dummy variables from that, and then this is a variable with 8 categories, so when you put it in the model like this, it's going to be 7 dummy variables, right? That's what it's going to do. It also has the variable Apache and Charleston. They're being controlled for, these other variables, and it's got the exposure variable in here. So that's how you run this, okay? And you notice you don't see glogit. Why don't you see glogit? Because you're not doing Polytomous logistic. You're doing the proportional odds model using an ordinal logistic regression approach. How does it know to do ordinal logistic regression? Because there are 3 categories, not 2. So the computer, just like Daniel said, there's more than 2 categories. So there you go, Daniel. Now you're in trouble. I'm going to call on you every time. No, not necessarily. Okay. So, okay. See, you pay for it. Pay for being good. I don't know. Okay. So again, I showed you the model. I showed you the formula for the model when there was only one exposure variable. Okay? For the model, the data set where there was just doing the crude data, 3 by 2. But this is the general formula for the proportional odds model. How have I changed things? Well, it's a little bit more complicated. The left side is the same, right? Probability y equal to greater than g. Okay, given x. X is the number of predictors, the collection of predictors that are on the right-hand side. Okay, You see the alpha sub g over here, right? Same thing as before, because it's got as many subscripts as you have one less the number of different categories. Still one less the number of different categories. And then on the right-hand side, you've got regression coefficients times a bunch of predictive variables. But what you may notice, you see it says beta j over here. But you don't see a little subscript g. It doesn't say beta jg. So there's only one coefficient for each different predictive variable. That's what this says. And that's what the ordinal logistic regression model does. And now, because you have g categories, and therefore g goes from 1 to g minus 1, you have more than 2 alphas, and each one of these alphas, alpha 1 to alpha 2 to alpha g, the first alpha is larger than the second, large, and so on. So that's the general formula for it. Okay, and it just allows you to say, and you noted the key thing about this is that there's no g subscript on any of these regression coefficients. So if you're going to get an odds ratio for any one of these let's say one of these is exposure and the others are variables you're controlling for, then it's going to be a single odds ratio. You're not going to get several odds ratios that you would get if it was polytomous. Okay, so in fact, here you go. This is the model. I'm just doing it again, showing it again. This is the proportional odds model, how it would look for the AC study. Okay? It's 1 over 1 plus e to the minus alpha sub g, and it's got those AC status, Apache, Charleston, and those 7 dummy variables. That's what this model, that's what it translates to for the data set that we're doing the analysis on. Okay? And you notice, for example, the AC status variable just has a single coefficient. So for this model, which is a no interaction model, right? It's a no interaction model because you don't see anything exposure times a control variable. So what's the formula for the odds ratio for the effect of AC status? It's e to the beta 1. So you fit this model and you get beta 1 hat and you exponentiate it. If you want to test a hypothesis for it, you do a wall test or a likelihood ratio test. You want to get a confidence interval, you get the usual confidence interval formula for it. And it's not that much different than binary logistic regression in the sense how you deal with it, because you're only getting an e to the beta type of answer to this. Okay? And now, but e to the beta in this case is an average of the different odds ratios you get if you took the pie and you cut it up in different ways that you're allowed to cut it up, and you control for the other variables that you're putting in the model. That's what this is. Okay. Now, I want to explain something else here. Why are the alphas, why is alpha 1 greater than alpha 2 greater than alpha g minus? There's a little algebra you can do to prove this, just to show you that you can do this. Okay. So first of all, this is when you're talking about the probability that y is greater than or equal to g. You can write that the probability that y is equal to g, plus the probability that y is equal to g plus 1, plus probability and so on, until you get y plus the probability that y equals up to capital G minus 1. So it's the sum of all these things, starting with g, because that's the lower bound of this expression. Okay. Now, if you're talking about, that's in general, but if you're talking about what's the probability that y is greater than equal to 1, then you start with 1, then you go to 2, and you go up to g minus 1. When you start with probability y greater than equal to 2, you're starting with 2, not with 1. Okay? Now, and when you go up to, well, as you can see from this, there are more terms here than there are here, right? So this term is in this formula, but it's not in this formula. So this thing has to be larger than that, right? Big deal, right? Probably y greater than 1 has to be larger than big deal, So now what that means, and I haven't proved about the alphas because it's a little tricky, okay? Now what it means is that if you look at the expression for what the formula is, I've now written if the probability of y greater than 1 is greater than the probability of y is greater than or equal to 2, I can take this expression, put in alpha equal alpha sub 1, and I can put alpha sub 2. This has got to be greater than that. It's got to be greater than alpha 3. This follows because of what I've just written here. Okay? Well, does that prove that alpha 1 is greater than alpha 2? No, because there's more algebra to do. Okay? And I'm just going through the gory details of the algebra. Okay? Now I'm just now focusing on the first and the second alphas. So what I've just shown here is that this one's greater than that. So I just wrote it up here again. This one's greater than that. Well, if this is greater than that, then what the next line's got to be true also. What have I done with the next line? I've inverted this. This is 1 over something, and this is 1 over something. And I just sort of looked at the denominators. You know, if 1 over this denominator is greater than 1 over that denominator, and I just look at the denominators, then this denominator has to be greater than that denominator. We'd have to switch the 2 with the 1. That's just algebra, okay, which you knew before you got into the MPH program. Maybe, I don't know. Yeah, well. And then you go on. Well, you look at this thing. If this is true, okay, then this next statement has to be true, right? Because the only difference between what's here and what's here is there's a 1 here and there's a 1 here. It's the same 1. So this has to be true, okay? Well, if that's true, and the only difference between what's here and here is this extra term to same extra term. So I can write e to the minus alpha over 2 is greater than e to the minus alpha over 1, alpha sub 1. That's just algebra, okay? And if that's true, e to the minus something is greater than e to the minus that, then I could, this is like 1 over e to the alpha sub 2, and that's 1 over e to the alpha sub 1, and I could rewrite that and say, well, then e to the alpha sub 1 has to be greater than e to the alpha sub 2, and therefore alpha 1 has to be greater than alpha 2. Big deal, okay? So that's why the alphas follow, you know. If you never really thought of that, that's how it follows. You never have to do this again, maybe. And I'm just showing you that. Okay, now, it's another thing I want to show you here. Okay, now, the model, remember, the formula for the model, this was the formula. This was the formula I showed you down here at the bottom of this screen, right? Probably y greater than or equal to g is 1 over 1 plus e to the minus, this thing, where there's the alpha sub g, but there's no g's here. Okay. Well, there's an equivalent way I can write this model. An equivalent way. It's a logit formula. Remember when we talked about the logistic model? There was a way to write the probability formula, and there was a logit way to write the model. And there were two equivalent ways of saying the same thing. Well, this is the logit formula of the model. Now, think about this. Is this a logit? This is a log of something over something. Okay? When you're talking about a logit, the log of an odds, what's an odds? A p divided by 1 minus p, right? That's what an odds is, a p over 1. Now, is the denominator 1 minus the numerator? As they say in Georgia, show enough. Right? Yes. Right? If y is greater than or equal to g, the opposite of that is y is less than g. So this is an odds. This is a log odds. And if you take the log odds, if you take the odds, if this is the odds and the log odds is equal to that, it just follows, then the odds is equal to this. That's what the odds is. Okay? The Wizard of Odds. Okay, so that's another way you can write the formula. You can write it in the log. So you can either do it this way, or you can do it, you remember when you did logit, when you're doing for binary logistic regression, you just had the linear part of the model. Well, that comes out when you write the logit form of the proportional odds model. Okay, so there's two ways to write it. Now, this is not that important, what's on this slide. It turns out that when you're running, we're all using SAS, right? But some of us like other programs. Does somebody like other programs? What other programs do you like? Well, there's another one called Stata. There's another one called R. There's another one called SPSS. There's other different programs. If you use Stata, they use a different form of the model. And it's a little tricky, but I'm just saying that. I'm not going to go further with this because we're going to emphasize SAS in here, even though if you're using Stata, you've got to be a little careful. The model's a little different, and the alpha sub g's in the Stata model is minus the alpha sub g's in the SAS model, but the betas are the same. Anyhow, now here's what I want to talk about. This relates to the proportional odds assumption. Okay, now this expression, this over this is the odds. The odds for y being greater than g is probability that y is greater than g over 1 minus the probability that y is greater than or equal to g, which is probability y is less than g. Okay? And that's equal to this. I've just showed you that. Just showed you that on the previous slide. Just showed you that on that slide. So if that's true, and this is the odds, okay? Now, suppose we talk about an odds ratio. Not an odds ratio. This is a formula for the odds for an individual has a certain set of values of the predictors. Now, suppose we have two individuals, just like when we talked about an odds ratio when we're doing binary logistic regression. Suppose you have two individuals, an individual X star and an individual X. And this is the formula for an odds for any one individual, but we want to look at the odds for these two individuals. We want to get the ratio of those two odds. So if we're comparing X star with X, then the odds for the individual for X star divided by the odds for individual, that's just writing that. The odds for one person divided by the odds for the other person. Well, what's the formula for each of these two odds? Well, here's the formula for the X star person, and here's the formula for the X person. All I've done is taken this and put it in it, but I put an X star in here because that's X star person. The X's might be different, okay? And that's the X person. So if I do a little algebra here, what do you notice about when you do the algebra and you get this expression? What's not in this expression? The alpha's not in there. And there are several alphas, but they drop out, right? That's what you get. You get an expression for the odds ratio that doesn't depend upon the g. You get an odds ratio expression that's independent of how you've cut the pie. Doesn't matter how you've cut the pie, how you've split up the big table into subtables, even though there's a number of different ways you could do it. So the odds ratio comparing two different covariant vectors, X star and X, is independent of the category of G. Now, where does the proportional odds, where does that term come from? Well, you go to the next slide. Well, it's true that the ratio of the odds for one person divided by the odds for the other person is equal to a value that has nothing to do with G. It only depends upon the two X's of these two individuals. Nothing to do with G. So if you say, well, if A over B equals C, then A equals to B times C. That's just a little algebra too. So the odds for X star is equal to this number, some value that has nothing to do with G, times the odds for individual X. Well, that's a way of saying that you can get one odds for one person from the other odds by multiplying it by some number that only depends upon the two people but doesn't depend upon how you've cut the pie. That's why it's called proportional. This odds is proportional to that odds because you can get one from the other and not worry about how you've cut the pie. That's what this says. That's what the proportional odds assumption says. Another way of saying it is that when you get an odds ratio, when you're doing Polytomous ordinal logistic regression, it's not going to depend upon G. That's another way of saying the proportional odds, what that means. It doesn't depend upon G, the way you can split up your categories into different ways. One versus the others, or 1 and 2 versus the others, or so on. So that's what the proportional odds assumption is. Now, let's see if there's anything. Okay, so here's the let's look at the data and the result for the data, okay? So here's the, by the way, how are we doing with this? Am I doing all right with this? I mean, you following this? Should I have gone faster? Should I go slower? Well, can't go any slower because we'll never get out of here. Okay, so here's the model again. I've shown you this model, okay? The model has several different alphas, but it only has a beta for each different variable. So I run this model, and this is what I get. This is the output when I run the model using proclogistic, using the coding. This is what I get. Now, what do you notice about this? I get two coefficients for the intercept, right? Two different intercepts I'm getting, okay? How many coefficients do I get for AC status? One. How many do I do for every other variable in the model? One. Because those variables, the predictive variables, don't have a subscript, okay? Now, why did I put AC status in bold? Because that's the exposure variable and it's a no interaction model, right? So for this model, if I wanted to get the odds ratio for the AC stat for the exposure, well, how do I do it? What do I do? I exponentiate this, and it controls for everything else in the model, right? And that's what's on the next slide. The next slide has the AC status e to the beta. It's 1.987. And it's e to the beta for all these others, but we don't care about these other e to the betas. We only care about this 1.9. I should have only had this one in bold. I shouldn't have had the others in bold. Okay? 1.987, that's the confidence limit. You can also, can you see from this the wall test? Is it significant? Is the wall test significant? Well, not at the 5% level. It's a two-tailed test. Okay? Two-tailed test is not significant. What about the one-tailed test? How do you do what if you wanted to do a one-tailed test for this? Would it be significant? How do you do a one-tailed test from a two-tailed? What do you do with the p-value? You multiply it by 2 or you divide by 2? Divide by 2. Is the one-tailed test going to be significant? Yeah. So maybe you have something, depending on what you want, whether it's one-tailed. How do you decide whether it's a one-tailed or a two-tailed? Do you decide based on whether you get the result you want to get? No. Okay, good, thank you. I won't say any more than that. Okay. So, okay. And you notice that the 95% confidence interval is wide and includes the null value, but the lower limit is 0.930, which is pretty close to 1. So it's sort of borderline significant. You can say, well, you know it's borderline significant, but this is the wall test. Maybe the likelihood ratio test might actually be significant. But anyhow, that's what you get. And you can say, well, it looks like maybe when you control for all these other variables, people who are resistant are more likely to, well, no, what's the outcome? The outcome are more likely to have a longer stay in the hospital. That's what you're worried about. I mean, the outcome is, you're saying if you're resistant, are you more likely to stay in the hospital than if you're not resistant? That was the question. Okay, you always got to go back to the question. I mean, you can get lost in all the stuff we're doing, but that was the question. It looks like there is a moderate effect here. I mean, this is almost 2. It's borderline significant, not significant with the confidence interval. Significant if you take if you do a one-sided test. So that's how you do it. Okay, and that's well, I'm not even going to talk about this because mainly I wanted to talk about how you do it. So that's ordinal logistic regression. Okay, so with that, now what I want to do is what I also did is I changed the last couple of slides to try to help explain some things a little bit more. Now, what I'm now going to show you in these next few minutes is just sort of a summary of what we've just done this class and the last class. A summary of Polytomous and Ordinal, just writing what we're talking about, more or less, okay? So suppose you have a situation where you've got, and it's a summary, but in a simple way, you've got 3 categories of the outcome, and you've got a binary exposure variable, and suppose you have 3 variables that you want to control for. And they're all, age, race, and sex, and there's no subcategories. You don't have 8 categories of a matching variable, whatever, or 8 categories of some other variable. You just have 3 variables, and let's say they're all binary. So here's a model, and I said polytomous. Can you tell that this is polytomous? How do you know that this is polytomous? Well, one way to know is you see you got a g on every coefficient in the model, right? See that. And you notice the model is the log of p of y equal to g compared to p of y equals 0. So you're comparing one category to a reference group. Okay? So in this case, g is 1, 2, so it's 2 versus 0 and 1 versus 0. So that's a polytomous logistic regression model. And if you wanted to test, just to review what you have to do, if you want to, this is a model that has, you see it has some interaction terms. Products of E with C's, right? So this is an interaction polytomous logistic. So if you wanted to test for the interaction in this model, you'd be testing whether the coefficients of these interaction terms are equal to 0, right? How many terms do you have? Do you have 3? You have 6. Why do you have 6? See, it says delta JG, okay? And G goes from 1 to 2. So there's 3 deltas for each of the different G categories that you're comparing to the reference group. So there's 6 deltas. So the null hypothesis to test for interaction is that all 6 deltas, I wrote delta JG, J goes from 1 to 3, G goes from 1 to 2, it's a chi-square with 6 degrees of freedom. So if you're doing a test for interaction here, it'd be a 6 degree of freedom chi-square test. Okay. And if you're doing the likelihood ratio test, the full model is this, and what's the reduced model? Same old stuff. What's the reduced model? It doesn't have these terms in here, these product terms, for both versions of the model. This way of writing it has 2 components to it, because G is 1 and 2. You remember I said you got as many components as you have 1 less the number of categories. So this model, for the reduced model, won't have these different product terms. Okay? And so it's the likelihood ratio test would be the minus 2 log maximized likelihood for the reduced, minus 2 log maximized likelihood for the full. It's chi-square with 6 degree of freedom. Now, what I added to this is that if this test was not significant, this wasn't in the original thing, if this test was not significant, this model would reduce to this model, right? Because I'm dropping the product terms. Just want to make sure you know that. And for this model, the formula for the odds ratio for the effect of exposure, would be this. So you'd get several odds ratios. You wouldn't get a single odds ratio because you've got 3 categories. So you're comparing one category to the referent and the other category to the referent. So you're going to get 2 odds ratios. So that's the formula, e to the beta sub g. That's when it's polytomous. Okay? What about this next slide? Now, this is an ordinal logistic regression model. Right? Well, one way you know it's ordinal is you look at the right-hand side, and even though you see a G here, you don't see any G's here. Right? It's one way to tell. But the other way you have to tell is, well, what's this left-hand side? What's this? This is the log what? This is one way to write the model. This is the logit form of that model. The logit is linear if you're using proportional odds. I could have written it as a probability of y greater than g, then it would be 1 over 1 plus e to the minus, but I've written it in a way that the right-hand side is linear. And again, this has interaction terms. That's the ordinal logistic proportional odds model. That's the formula for it. And it turns out for this model, here's the formula for the odds ratio because it has interaction terms in there. It involves the coefficient of the exposure variable and the coefficient of any product terms that involve exposure, just like it did when it was binary logistic regression. This is the same formula that we use for binary logistic regression because you don't have to worry about the alphas here when we're getting an odds ratio. Okay, so that's ordinal logistic regression. You want to test for interaction. you're testing whether these terms can drop out, testing whether you can get rid of these three terms. So the null hypothesis, now you only have 3 deltas, you don't have 6 deltas. Okay, so you're testing whether delta 1 equal delta 2, delta 3 is 0, and the full model is this model. The reduced model doesn't have these product terms in there, and it's a chi-square test with 3 degrees of freedom. Reduced minus the full, chi-square with 3 degrees of freedom. And if it turns out that test was not significant, this model would reduce to this model. There's no product terms in this model. And for this model, the formula for the odds ratio for the effective exposure is just e to the beta. Like it would be in binary logistic regression, except you're doing something extra because you have an outcome that's ordinal. So you're making more use of that in doing this analysis. So that's what ordinal logistic regression is, and how it differs from Polytomous. It's the same as binary, only a little different. You know, you just have to get used to these little differences here, but it's not that bad. Okay. When you see the practice exams, you're going to see the practice exam focuses primarily on either Polytomous or ordinal and asks a whole bunch of questions on it. It doesn't do a binary logistic regression model. I mean, that's a whole hat now, in some sense. So the practice exams and your midterm is going to focus more on these two, because we're really doing the same thing. It's just a little bit, another slight level up. Now, one last thing. Now, look at, this is the last thing. I may have some other things to say, but this is the last thing I want to say about this issue, what I'm doing here. Okay. Now, again, this is the formula for the ordinal logistic regression model, and this is the logit formula, right? The logit formula. And this is the formula for the log odds. It's not the formula for the log odds ratio, it's the formula for the log odds. So there's odds and there's odds ratio. An odds ratio is the ratio of odds. The odds is something for an individual person. There's an odds for one person and there's an odds for another person. So what if I actually wanted to do what if I asked, if this was the model and I asked what's the odds that y is greater than or equal to 1? What's the odds for a person for any person, x, that y is greater than or equal to 1? And then I'm asking, what's the odds for that same person that y is greater than or equal to 2? Well, if I did, I'd write the odds for y greater than 1 like this. If I write it for y greater than 1, write it like this. These are the two formulas that I get for y greater than or equal to 1, y greater than or equal to 2. Now, you remember I said the odds ratio doesn't depend on how you cut the pie. But what about the odds? If I'm comparing for the same person, two different odds, same person, person X, there's no X star here. Looking at person X, and I'm comparing the odds for y greater than 1 versus the odds for y greater. Which one of these, are they the same? Why aren't they the same? Because this has got alpha 1 and this has got alpha 2. Which one is larger? This one, because alpha 1 is greater than alpha 2. We already went through that. Okay? So if you're comparing odds instead of odds ratios, you can talk about for a given person, one odds is different from another. If you're dividing one odds for one person with the same odds for another person, then you could be talking about an odds ratio that won't depend upon the alpha. But when you're talking about odds, you do get something. So there's going to be something, when you look at the practice exam and and you actually get the exam, there's going to be a question like this about odds to ask you some question related to this formula. So that's pretty much, now if I click on the next slide, what happens? Okay. So I've just finished with that. Okay. Now, it's 5:15. Okay. Should we stop? That's what I figured. Have you had enough? Okay. So before we stop, let me say, what have we done? What have we done up to this? We've done Polytomous and ordinal logistic regression. Okay, right? That's what we've done in the last two classes. Prior to that, we did modeling strategy. Well, really, it applies also to polytomous and ordinal. You can still talk about how do you get the right model, even if it's a polytomous or ordinal. So we've done modeling strategy, and we talked about modeling strategy for a nice, simple situation. You had a single E and no interaction. We talked about modeling strategy for a single E and there was interaction. And then we started talking about modeling strategy for several E's, okay, which got more complicated, okay. So on Tuesday, I'm going to say a little bit more about that, kind of review some of the things that we've said. And one of the things that was a little complicated was what happens if the model that you get at the end of everything only involves E's, like you have 2 E's in there or 3 E's, and you want to come up with the best model. How do you do that? Well, that was talked about in the lab, but it's still a little bit something we talk about a little bit more, right? What do you do? And there's a lot of options, and no option is necessarily better. You know, none is exactly always right. There's different ways to do it. So I'll talk about that a little more on Tuesday. And the other thing I'm going to talk about on Tuesday is something that's not going to be covered on the exam, and that's what the next topic is. It has to do with collinearity, okay? And that's an important topic, and that topic is going to be on the following exam. So if you come to class and I finish talking about the strategy review, and then when I start talking about everybody has a mass exodus, you know, well, I can't stop that, but it's on the next exam, so it's up to you. So, you know, and again, of course, we're recording this, so do you have to come to this class? It's on recorded. Well, it's probably a good idea to come to class and then listen to the recording, because then you hear it again, and you can stop it and play it back, but everybody's different. So you go for it any way you want to, okay? See you on Tuesday. And you got stuff to do this weekend, don't you? I thought so. Sorry, but that's life in graduate school, right? Okay. This is Megan. No, this is not Megan?
Yeah.
It is Megan. That's who I saw before. Okay.
I just have a question.
Let me just do something before you ask your question so I can